Hello, chemistry students. Mr. McKee here, and we're going to talk about how to draw Lewis dot structures. Lewis dot structures give us a way of representing the electron structure of an atom and understanding how atoms bond together to form molecules and compounds. We can also use them for individual atoms, and we'll touch on that here briefly. First thing that we need to review is something we talked about in our last unit, which is valence electrons. So we're going to go to the periodic table. And across the top of the periodic table, we see all of these numbers, and these are the group numbers, you will recall, hopefully. And by looking at the group numbers, we can tell how many valence electrons a particular column on the periodic table has. I want to remind you also that in first year chemistry, we pretty much ignore all of these transitional metals. Okay, so we won't talk about them in this case. They are more complicated in just about every respect. But if we look at group 1 here, all of these elements in this column have one valence electron. Group 2, all the elements in this column have two valence electrons. And I'll remind you also what a valence electron is. If we look at this diagram, we see the valence electrons are these electrons found in the outermost orbital. Okay, so we ignore all the inner electrons. We're just looking at the outermost orbital. And we can do that because it's these valence electrons that are most responsible for the chemical bonds that atoms form and also for the properties of an atom. So they are the most important the most important electrons in an atom. Okay, so back to our chart here. When we skip across the transitional metals, we pick up here in group 13, and you might think, well, these have 13 valence electrons, but no, we ignore the 1, and all the atoms in this column have 3 valence electrons. And then in group 14, they all have 4 valence electrons. Group 15, 5, group 16, 6, group 17, 7, and finally group 18 all have 8 valence electrons, which is the maximum number of valence electrons that an element can have. And I will remind you also that these group 18 elements, known as the noble gases, these are the most stable atoms on the periodic table because atoms really want to have a full valence shell, and these noble gases have a full valence shell. So that means they're also not going to interact with other atoms because they are happy on their own. Okay, so let's talk about Lewis dot structures for simple atoms. So I'm going to list a couple of atoms up here, and we're going to draw the Lewis dot structure for 3 of these atoms, and this is pretty straightforward. So let's start with oxygen. Let's check the periodic table to find out how many valence electrons oxygen has. We see it right here, and it's in group 16, which means it has 6 valence electrons. So we're simply going to put 6 dots around the oxygen, and in no particular order, the first 4 dots should always go north, south, east, and west. So again, it doesn't matter the sequence that I do that, but we want one on top, one on bottom, and then one on the sides. And you can kind of picture there being a square around the atom, and that's where we're going to put our dots. So remember, oxygen has 6 valence electrons. We've only put 4 in there, so now we're going to start pairing up electrons on the side. Doesn't matter which ones we pair up. I could do the top and the bottom. I could do the top and one of the sides. I could do both sides. Let's go with that. So I'm going to pair up electrons on the sides here, the east and west, if you want to think of it that way. So you should never have more than 2 electrons per side when you're doing these Lewis dot structures, and that is the Lewis dot structure for the atom oxygen. So let's look at nitrogen. Again, find it on the periodic table. It is in group 15, right next to oxygen, and it has 5 valence electrons. So again, my first 4 are going to go north, south, east, and west in no particular order. and I have a fifth electron I need to add, so I can pair up any of these electrons. I'm going to pair up the one on the bottom, and that is the Lewis dot structure for nitrogen with its 5 valence electrons. Carbon is next to both of these on the periodic table, and it has 4 valence electrons. It's in group 14. So we can simply put the first 4 on here, north, south, east, and west, in no particular order, and that is the Lewis dot structure for carbon. Okay, so this is for individual atoms. And one thing you'll notice is that all of these atoms are a little bit unhappy, okay? Because they don't have 8 valence electrons around them. And that is what atoms want, is 8 valence electrons. They want to complete their octet, is what we say. So that is something worth keeping in mind here, that these atoms are all somewhat unhappy. That means that they're going to want to pair up with other atoms in order to share electrons and fill their valence shells. So we're going to explore how they do that here with Lewis dot structures for molecules. So if you go to your book, the page may vary from year to year, somewhere around page 19 here in 2025. You can see these steps for drawing Lewis dot structures for molecules. And I'm going to walk you through these steps. So let's do that now, and we're going to do a couple examples. So the page after those steps, you're going to see a few examples here. Let's consider the molecule water, H2O. Step 1 is to count up the valence electrons for water. So we're going to break it into its parts. And H2O has 2 hydrogens and it has 1 oxygen. Hydrogen has 1 valence electron. Oxygen has 6. We just talked about how to figure that out. That's pretty critical. But we don't have just 1 hydrogen. We have 2. So we're going to take 2 times 1. And we have a total of 2 valence electrons in the molecule water. We just have 1 oxygen, so that's 1 times 6. We add these 2 together to get 8 valence electrons. So that is step 1. Step 2 is we're going to determine the central atom. And here's kind of our rules we use. And usually the first rule is going to be just fine, the first and the second rule. The first rule is usually the atom of which you only have 1. And the second rule is it's usually going to be carbon if carbon is present. And in fact, I think it's pretty much always carbon. And it's never going to be hydrogen. So let's look at water here. Well, we only have 1 oxygen molecule. So that means that's going to be the central atom. And again, hydrogen is never going to be the central atom. So we're going to start drawing our molecule, and we're going to begin with oxygen in the middle. And we are going to connect it to 2 hydrogens. So let's go back to our steps, and we just did step 3. We're going to draw single bonds to the central atom. So let's make sure everybody understands what these bonds represent. So these lines that I drew here represent covalent bonds, and each line represents 2 shared electrons. And they're equally shared between the hydrogen and the oxygen molecule. Okay, and that's true on both sides here. So each line, one more time, represents 2 shared electrons. So at this point, we have used 4 of our 8 valence electrons. So I'm going to do a little counting over here. I suggest you always do the same when you're solving these kinds of problems. That leaves us with 4 valence electrons to use. Okay, now step 4 is we're going to put all remaining electrons on atoms as lone pairs. Okay? And then we're going to ask ourselves if all of the atoms are happy. All right? So let's go back to our example. I've got 4 valence electrons. I'm going to add them where they are needed. The hydrogens are happy because, remember, hydrogen only wants 2 valence electrons. Hydrogen and helium are the exceptions. All the other atoms want 8 valence electrons in order to be happy. So my hydrogens are happy, but the oxygen is not, because we've only got 2 electrons here and 2 electrons here. So that gives oxygen just 4 electrons around it. So we're going to simply add 2 pairs of electrons as lone pairs, and then that's going to give us 8 electrons around oxygen. And you can visualize it this way by kind of circling oxygen's electrons. And we got 2, 4, 6, 8. You'll notice that I always count by 2s with electrons because they pretty much always occur in pairs. So then we ask ourselves, are all these atoms happy? And indeed they are. Hydrogen has 2 electrons around it. This hydrogen, same thing. And then oxygen has 8 electrons around it. So we've got a happy molecule. You don't need to go on to step 5. Let's move to example 2 here, where we're going to see step 5 employed. We've got sulfur trioxide. So it's got 1 sulfur and 3 oxygens. Both sulfur and oxygen have 6 valence electrons. 1 sulfur means that it contributes just those 6 valence electrons. 1 times 6 is 6. And then the 3 oxygens, 3 times 6, make 18. That's how many valence electrons those 3 oxygens are contributing to the molecule. That gives us a total of 24. So then we ask ourselves, step 2, what's the central atom? And it's the one that we only have 1 of, which is sulfur. And step 3, we're going to start with single bonds between sulfur and the oxygens. So each single bond represents 2 shared electrons. So we have used 2, 4, 6 of our 24 valence electrons, and that leaves us with 18. Okay, step 4 is to add these 18 valence electrons as lone pairs where they are needed. So I always like to start on the outside. So I'm going to go 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay? And I am now out of valence electrons, which is a very important thing to understand as we move forward here. So now, as part of step 4, I ask, are all these atoms happy? And the answer is that all of the oxygens are happy, and we can visualize that this way, where we've got 6 unshared electrons and then 2 shared electrons that add up to 8. Same thing on this oxygen, same thing on this oxygen. Remember that each of these bonds represents 2 shared electrons. Okay? So the problem is the sulfur is not happy. It only has 6 electrons around it, and it wants 8. So you might be tempted to just add 2 electrons to it, but remember, we are out of electrons. So what is the solution? Just like when you have 2 people and only 1 blanket, you're going to have to share the blanket. In this case, we're going to have to share electrons. So I'm going to take 2 of these unshared electrons, and I can take them from any of the oxygens, and I'm going to slide them over between the oxygen and the sulfur, and they're going to share those electrons. So now that oxygen still has 8 around it. It's got 4 unshared and then 4 shared, and now the sulfur has 8 around it, all of which are shared. But remember, shared electrons are just as good as unshared electrons. So that was step 5 that I just did when I added a double bond as needed. Okay, and we only do step 5 when we have unhappy atoms after step 4. So pause the video and try the next 2 examples on your own, and then I'll go over them with you. Okay, welcome back. I'm going to quickly move through these examples here. So this compound, which we don't have an easy name for, has 1 carbon, 2 hydrogens, and 2 chlorines. So carbon has 4 valence electrons, hydrogen has 1, chlorine has 7. We've got 1 carbon, 1 times 4 is 4. We've got 2 hydrogens, 2 times 1 is 2. We've got 2 chlorines, 2 times 7 is 14, and those add up to 20. Carbon always goes in the middle if it's present. So I'm going to start with that, and then I can place the other 4 atoms anywhere I want around the outside. It doesn't matter. I'm going to put a chlorine here and a chlorine here, and then I'll put the hydrogens on top and on bottom. So at this point, I have used 8 electrons, and those all come from the 4 single bonds that I have used. Each single bond, remember, counts for 2 electrons. So that leaves me with 12 valence electrons to work with, and I'm going to add 6 to each chlorine to complete their octets, and that uses up all my electrons, which is fine because now as part of step 4, when we look at each atom, we will see that they are all happy. Both of the chlorines have 8 electrons and both of the hydrogens have 2 electrons. So we don't need to use step 5 in the case of example 3 here. Example 4, let's check it out. Carbon dioxide, CO2, very important and famous molecule. Carbon again has 4 valence electrons. 1 times 4 is 4. Oxygen has 6. 6 times 2 is 12. That gives us a total of 16 valence electrons. Remember, carbon always goes in the middle. And then for step 3, we start with single bonds. Now we have used 4 of our 16 valence electrons. That leaves us with 12. And I'm just going to start adding those 12 valence electrons. This is step 4 to my outside atoms here. 2, 4, 6, 8, 10, 12. So if you look at this, you'll notice now that both oxygens are happy. They both have 8 valence electrons around them. But the carbon is not happy. It only has 4 electrons around it. And the trouble is we are now out of valence electrons to work with here. So we can't simply add more to the carbon, so we're going to have to do some sharing. Remember, that's what you do when you run out of electrons and you still have unhappy atoms. You have to share more. So I'm going to, first of all, move those unshared electrons over here. And then I'm going to add things up. So now my oxygens are still both happy, but the carbon still is unhappy. It only has 6 electrons around it. So I'm going to do the same thing to the other side. Take those unshared electrons and make them shared, and now everybody's happy. This oxygen has 8 around it. This oxygen has 8 around it, and my carbon has 8 electrons around it. So as always, reach out if you have any questions. Good luck. Have a great day.